Well, I have to play a little bit of a tribute to John Lennon and Imagine, since we'll be talking about imaginary numbers today and doing a review of different properties of complex numbers. So, to begin with, this is going to be review material primarily for everybody, hopefully. So, we're going to be looking at the idea of a complex number. And to start with, we have what we call the imaginary unit. The idea, the motivation behind imaginary numbers is said to have resulted possibly from trying to solve this equation. So if you went historically back in time and someone was asked to solve this equation, they would probably just say nonsense. That equation doesn't make any sense. So the idea kind of is, you can't find a number, a real number, and square it, then add 1 to it and get 0. So you're out of luck. You won't find anything. So it was imagined that such a solution existed. And if I went through and plugged in the square root of negative 1, and if I did the square root of negative 1 and squared it, plus 1, then, okay, we kind of are familiar with the idea that if you square a square root, the radical comes off. So it looks like that is probably a solution to that problem if we imagine that the square root of negative 1 exists. So we developed a number system out of that we call the complex numbers, okay? So basically a complex number consists of two parts. It's got the real part, A, and it's got the imaginary part, BI. A and B are real numbers, and I is the imaginary number. Okay, so we would say that A is the real part, B, I is the imaginary part, okay? So they are combinations of imaginary and real numbers, all right? So to begin with, we just want to take different situations and identify the real and imaginary part. So to begin with, if you had the number 10, 10 is a real number, you could write that as 10 plus 0i. So the real part would be 10, then the imaginary part would be 0i. Okay, if you had 4 pi, well, that is a real number, so that would really be saying 4 pi plus 0i. So the real part is 4 pi. The imaginary part is 0i. So any real number can be written as a complex number because you have the 0i part. All right, this one is already in the standard form of a complex number, so your real part is the negative 3. Your imaginary part is the 3i. Okay, and then we got one last illustration here. If you had something like this, you have a square root of a negative number, so you could write this really as negative, and then you could take the square root of negative 1 out, so you can factor that square root of negative 7 like that, and then you could replace this thing with I. So you would have negative I root 7. So that could be written as 0 minus I root 7. So the real part is 0, and the imaginary part would be negative I root 7. Okay, so that's what complex numbers are. That's the idea and the definition. So one of the things we want to do in this section is we're going to do a lot of review of different things with imaginary numbers. So to begin with, if you had the square root of negative 25, again, we imagine such a thing to exist. We can actually break this up into the square root of negative 1 times the square root of positive 25 by using basic properties of radicals. And then again, I can replace the square root of negative 1 with I. And then the square root of 25 is a real number, so that's 5. So this would be written as 5i. As far as a complex number, this would be written as the number 0 plus 5i. Okay? All right? Now, you can do a lot of these things in your head, so, but without going through all the details of this. So the next one, you would say square root of negative 1 times the square root of 36. Again, the square root of negative 1 gets replaced with I. Square root of 36 is 6, so we're left with 6i is the way to write that. And as far as a complex number, you could write that as 0 plus 6i. So one of the things that you want to get pretty comfortable with, if you aren't already, is if you saw something like a perfect square that has a negative under the radical, you can pretty well immediately just write it without having to go through the steps. So if you had square root of negative 64, that's 8i and so forth. So you're imagining that that square root of a negative number exists. Okay. All right, and then you can also do things like this. Like on number 7, you can break this up like we did the other two. So you can do this, and then again you can replace this with I. So you get, at the beginning, you get I times the square root of 234. And then you've got a background, and you've actually done this quite a bit in trigonometry. You've simplified radicals. So what I'm going to do on this without a calculator, I would like to remind people that sometimes you can do things like this. You don't need a calculator all the time. I know that this number divides by 2. Okay, so I would have 2 times 117 if I did that. All right. And then this divides by 9. The reason I know that divides by 9 is because the digits add up to 9. That's a divisibility rule for 9. So I'm going to go ahead and break that up into 9. So 117 divided by 9, that's going to go in, let's see, 13 times. Looks like 13 times 9 is going to be 27. Or 3 times 9 is 27. 13 times 9 is 117. Okay, so we got that. And what we have is a perfect square. So if you kind of look at this, one thing that you can do is we found a perfect square factor, then the other two things are prime numbers. So what we can do is we could break this up like this. We could say I times the square root of 9. Then we can put back together the 2 and 13. So if I put back together the 2 and 13, I get 26. So that means the final answer of this problem would then be, that becomes 3. So you want to write this as 3i times the square root of 26. Okay, like that. All right, and so that's how you would break up radicals. So it's the same principle, except you have a negative under the radical, so you have an imaginary number. Okay, now addition of complex numbers, you can think of that as just combining like terms. So we define addition like this. If we have a complex number a plus bi plus another complex number c plus di, then what we do is just add the real parts, and then we add the imaginary parts times I, like that. So that's how we define addition. So you can think of this as just combining like terms. So you're going to have 4 minus 4i plus 5 plus 6i. The parentheses are not necessary other than they're separated in the complex numbers. And then you can put together the real part. So if you add those two, you would get 9. Okay, then you can add the imaginary part. So negative 4 plus 6 is going to be 2i. So we have an answer of 9 plus 2i. Okay, so that's how you add complex numbers. Very simple. Subtraction can be defined in terms of addition. So you can think of this as the same way. So I'm just going to take off the parentheses. We'll have the complex number 7 plus 4i. I can distribute that negative through. I'm really subtracting a negative 3, so that's adding 3 and subtracting I. And then what I can do is combine the like terms together. So I've got 10 here, and then I got 4i minus I is going to be plus 3i. So I can write this as 10 plus 3i. Get that corrected there. Okay. So 10 plus 3i would be the sum of those two complex numbers. So that's very simple. Just think of that like combining like terms. Okay, the next problem is multiplication. And just to kind of review how multiplication goes on complex numbers, if you have the complex number a plus bi, and you're going to multiply that by the complex number c plus di, you can think of this as multiplying. You can think of it even as FOIL if you want to. So the first term, we're going to do the first term, which is going to be AC. We can do the outside term, which is going to be plus ADI. Then we can do the distributive property with the BI. So BI times C is going to be plus BCI. And then I can do the last term on the distributive property, so I end up getting plus BD I squared. Okay, so you just multiply that out like you do FOIL, but one of the things that's kind of a important part is the whole complex number system is built on two ideas, that I is the square root of negative 1, and then we define I squared to be negative 1. Those are the two building blocks of your imaginary numbers leading to your complex numbers. So we have those two things. So if we put this together and kind of go like this, we'd have AC. These things would go together, so you could think of that as AD plus BC times I, and then this thing right here is BD times negative 1, because the square root of, anytime you see I squared, that's going to get replaced with negative 1, because that's what it's defined to be. Okay, so you would end up having AC, and that's supposed to be a BD there. This whole thing would be minus BD. That would be the real part, and then the imaginary part would be AD plus BC times I. Okay, so that would be how you define multiplication of complex numbers, is to do that like that. Okay, now when you're doing this problem, you don't have to think about that formula. You can just think of multiplying it out then, which is what I'm going to do. So let's just take the 5 and distribute it. We're going to do 5 times 6, and then we're going to do 5 times 9, doing a distributive property. So 5 times 6 is 30. 5 times 9 is 45i. Okay, then we're going to do a distributive property with the negative 4i. So we're going to do those two multiplications. Okay, so I'm going to have negative 4i times 6 is negative 24i. And negative 4i times 6i is negative 36i to the second. Okay, you can think of combining like terms. If you want to think of it this way, you can do 45 minus 24. So I do that kind of at the side if I need to. 45 minus 24 is 21. So I'm going to bring down the 30, and then I've got these two things go together to make plus 21i. And then when you see the I squared pop up, which you will see on this, you're going to replace that with negative 1. Okay, so what you'll have is 30 plus 21i. Now you have two negatives multiplied, so that's going to be plus 36. Now you combine these two like terms, so 30 and 36 make 66, plus 21i, so that would be the appropriate result of multiplying those two complex numbers. Okay. Now one thing I wanted to show you on this, which is worth showing, is most of your graphing calculators will do complex numbers for you in some way. So it's good certainly to know how to do this by hand, but as you get into more advanced math, there are times when it's nice to just do it on a calculator when it's a part of a bigger problem or something. So you'll notice above the decimal point, there's an I. So if I was to go through, for instance, and just go second decimal point, then I comes up. Okay, then I can do different calculations. So what I was going to show you is any of these problems that we just did could be done in this way. So if I do number 9, for instance, I could just type in 7 plus 4 times I, close parentheses, subtract, and then I could put a new parenthesis and negative 3 plus I, like that, and then the same answer comes out. Whoa, did I type something in wrong? No, I'm okay. All right, 10 plus 3i, so that matches up. Okay, so you can do that. And then number 10, you could do this like this. You could go parentheses 5 minus 4i, okay, like that, and then parentheses next to each other. That would be 6 plus 9i, and it should calculate this out. Sometimes there's some exceptions. Sometimes it'll, if you have a 0i, it'll put that 0, it won't get it exactly as 0. So you'll see that sometimes. So that would be a way that you could do this on a calculator if you needed to. You want to know how to do this, obviously, both ways, though. Okay? All right, now, one thing I want to mention on this, a lot of times be careful about this kind of situation. So if you had something like 7 plus 2i plus 8 minus 3i, I sure see students multiply this out a lot. This is a addition problem, so don't FOIL this. I sure see students do that a lot, though. FOIL or multiplication, you're going to have your two parentheses right next to each other like that. So be extremely careful about that. Pay attention to what you're doing. All right, now what I was going to show you next is some of the powers of I and the way these things work out. So by definition, these are, like I said, kind of the building blocks. I squared is -1. Putting those two things together, you can get any power of I, and these things kind of run through a cycle, which is kind of interesting. So notice on I to the third, I broke that up into I to the second times I. Well, I to the second's -1, and -1 times I is going to be -I. And then I to the fourth, I broke this up as I squared times I squared. Both of those are -1s, so you end up getting 1 as an answer. So you'll kind of see these things cycle through I, -1, -I, and 1. Okay, and you can kind of think of, you have a positive I and you have a negative I, and they alternate. Then you have a -1 and a positive 1. They alternate over and over again. So if you got up to higher powers like I to the fifth, the way that I work out I to the fifth is I say I to the fifth is I to the fourth times I to the first. I to the fourth is 1, so that's 1 times I, so you're back to I again. So you'll have this cycle between I, -1, -I, and 1 infinitely like that. Okay, so we're going to do a couple of powers of I, and I'll show you some different ways to do this. One of the best ways to do this is to kind of break it up into 4s. So if you looked at this number 11, if I take 10 divided by 4, that goes in 2 times with 2 left over. And you can kind of put this together like this. So watch how I do this then. This is how I do this. So I'm going to write the I to the 10th as I to the 4th to the 2nd times I to the 2nd. And see what I'm doing is I'm basically just saying I to the 4th raised to that power and then 2 left over as a remainder. And the reason I like to do it this way is because I to the 4th is going to be 1. So now you've got 1 to the 2nd times I to the 2nd, and I to the 2nd's -1. So what you would end up having here is 1 times -1, or that answer of that problem would be -1. Okay, like that. So that's how I tend to do these, is break them up like that. So it turns out that the remainder is really going to tell you what the answer to the problem is, and I'll show you that in just a minute. Okay, so if I do the next one, I'm going to just take 7 divided by 4. That goes in 1 time with a remainder of 3. So the key thing is I'm going to work with these numbers and put them together like this. So I'm going to say, in this, I'm going to say this is equal to I to the 4th to the 1st times I to the 3rd. Okay, well, there's two things. I to the 4th is 1. I to the 3rd is -I. So I'm going to replace I to the 4th with 1, and I'm going to replace I to the 3rd with -I. So that means the answer to this problem is going to be -I. Okay, so that's how you put that together. Okay, and all these problems can be done pretty much in the same way. Now notice what happened is it was the remainder that made the difference. So if you kind of look at these last two examples, if I had a remainder of 2, then I'm going to get -1 as an answer. If I have a remainder of 3, looks like I'm going to have -I as an answer. So we kind of need to figure out what happens if I got a remainder of 4 and a remainder of 1. And what you're going to find is a remainder of 1 is going to give I, and a remainder of 4 is going to take you to 1 like that. So it's going to cycle through like those things. You can't have a remainder of 4, Brad. So what I meant is remainder of 0. Okay, so you get that. Okay, so the idea with all these is we're going to do these basically the same way with division. So I'll do 68 divided by 4 and do that division. So that goes 17 times. So what we do is we write this as I to the 4th to the 17th. Okay, and then when we do that, looks like this one has got a remainder of 0. Okay, so we would just do that, so we don't have to put the remainder of 0 there. So this is going to be 1 to the 17th, so that's equal to 1. So that would be an example of remainder of 0, just giving you 1 as an answer. Okay, then the next one, which would be one other thing that could happen if you do 69 divided by 4, go ahead and do that division. That goes like this. This time it's going to have a remainder of 1. So what you say is I to the 4th to the 17th times I to the 1st. You can see where all these things go. We're always breaking this up into I to the 4th to a power, and then whatever the remainder is. So what happens with this one is it works like this. Okay, again, I to the 4th is 1. So that's 1 to the 17th. I to the 1st is just I, so that's going to be 1 times I. So the answer to that problem is going to be I, like that. So that's how you can work out your powers of I. Okay, and your calculator will do these. Your calculator sometimes on these powers of I won't do these quite right. So, but you could go like I to the 10th on the first example. That gives -1, like we got. If I did I to the 7th on the second example, now see, this is what I'm talking about. The answer is -I, but notice how this thing right here is close to 0. So you'll get something like that. That's not the answer. That's just the way the calculator calculates this. So what it's really saying is -3 times 10 to the -13 minus I. And for all practical purposes, that's 0. So you get 0 minus I. So you'll see that sometimes on these calculators. The next one, you would go I to the 68th, okay, which gives, see, same thing. So that's why it's kind of interesting how this happens. So if you look at that, what it's doing is giving 1 minus this. So if you see this, you don't want to rely on the calculator. So you're getting 1 minus 3.2 times 10 to the -12 I. Again, that whole thing's 0. So for all practical purposes, that's 1. So you see that pretty frequently on calculators. If you're ever doing that, just kind of check your work. Okay, now going through, the next thing I want to do is just remind you of how division works in complex numbers. So what we do is it's actually equivalent to rationalizing a denominator. Technically, this problem can be thought of, remember, I is the square root of -1. So you could rationalize the denominator by multiplying by the conjugate of the bottom, which would be 6 plus 7 times the square root of -1. Now, you don't ever usually think of it this way. You just do what we call the complex conjugate. But you're technically just thinking of this as rationalizing a denominator. So the way we're going to do this is we really don't want to have this I in the denominator, since it's technically a radical. So we're going to multiply the bottom by 6 plus 7i. We call that the complex conjugate. And of course, we have to multiply the top by exactly the same thing. Okay, so we got to go through and do the multiplication and work out the details. So if I do the multiplication on the top, I'm going to have 9 times 6 is 54. 9 times 7i is plus 63i. Then distribute the 2i. 2i times 6 is going to be plus 12i. And then 2i times 7i is plus 14i to the second. Okay, now we go to the bottom, and you can do the details on that. 6 times 6 is 36. 6 times 7i is plus 42i. Negative 7i times 6 is negative 42i. And negative 7i times 7i is negative 49i squared. So what we're going to do is collect some like terms. And again, anytime you see this I squared pop up, those things are going to get replaced with negative 1s. Okay, So when we put this together in the numerator, we're going to have 54. Okay, those are like terms. So 63 and 12 is what? 75i. Okay, then this is going to be plus 14 times negative 1. Then if we go to the bottom, you're going to have a cancellation there. So you have 36 minus 49 times negative 1 like that. Okay, now what I'm going to do from here, just going to kind of bring this down. So I'm going to have really 54 minus 14 plus 75i. The denominator is going to be 36 plus 49. Okay, so what I have is 54 minus 14 is going to give 40 plus 75i. And if I do the denominator, let's see, 9 and 6 is 15. You got to carry, so that's 85. And then you want to break this up like this. So you want to say 40 over 85 plus 75 over 85i. So you want to write that as a complex number. And of course, you want to reduce the fraction. So you can reduce this by 5 over 5. You can reduce this also by 5. Okay, so then you get your final reduced answer. So you'd have 40 divided by 5 is 8. 85 divided by 5 is 17. 75 divided by 5 is 15. And then you would end up having this would be the way you'd want to write this final answer, is like that. Okay, and then this is a problem that you can check also on your calculator. Your calculator will do this. You just put it in like this. You'd do 9 plus 2i divided by, and then new set of parentheses. Be sure you do parentheses. So it'd be 6 minus 7i. And you'll get decimals on this like this. So what you can do, now some calculators do this, some don't. I've kind of seen. So if you go mode, and then go, go to the math button. So you want to press your math button. You can convert decimals to fractions. So sometimes if you put that in, it'll change that for you then. Okay, so you can do that as a quick way. Because what it was doing, it was using the decimal equivalent of 8/17. So you can use that as kind of a quick way to check answers on that. But you want to know how to calculate that out and run through the algebra. Okay, the next problem is really technically is the same idea. This is really just negative 5 over 0 plus 4i. Since that I is a radical, you really multiply it by the conjugate. You can think of it that way if you want to. But all you're really trying to do is just get rid of an I. So you could multiply by negative 4i, but you don't really have to. So I'm just going to do this like this. I'm going to say negative 5 over 4i. And I'm going to just multiply by I. Because if I multiply by I get I squared, which is negative 1. So what I'm going to get is negative 5i over 4i to the second. Okay, so that's going to give negative 5i over 4 times negative 1. So that's negative 5i over negative 4. The negatives divide out to give 5i over 4. And you can write the answer that way, or you can write it as 0 plus 5/4 I. If you're writing that in the complex form, then that would be the way you'd want to write the answer to that problem. Okay, so that's an example of division. So you really can think of that as rationalizing denominators. Okay, just to finish up with a couple of other little things. If you're multiplying complex numbers, one thing I want you to notice on this is it's wrong to do this. And you might want to write a note on this. It's wrong to just multiply these two things together, because if you did, you would get negative 13 times negative 13 is positive 169, and you get 13. 13 is not the answer to this problem. So you don't want to do it that way. You cannot do it that way, in fact. And what you have to do instead is you have to remove and write this in the imaginary form. So you're really writing this as negative 1 times square root of 13 times negative 1 times square root of 13. And you can bypass this step, because what you're going to have anyway is I radical 13 times I radical 13. Okay, and then when we do that, what you're going to have from here, I'm just going to move this up here, is you have I times I is I to the second. Then you can put these things together. Now you can put real numbers together under the same radical. So you could just write that as 13 times 13 like that. That's valid. But then I squared gets replaced with -1. And then if you're doing the square root of 169, you're going to get -1 times 13. So you get -13. So the answer to the problem would be -13 plus 0i. So notice you have a negative answer, not a positive answer. So what you're doing is you're taking two imaginary numbers and multiplying them together, and then you're getting a negative number. Okay, so the next one we're going to do in a similar way. We're just going to write this. Not much to do on this one. This one is 4i. So all you would do on this is just write this as 6 plus 4i, and it's done. There's nothing to do on that. Okay, and then this last one, we're going to do this like this. Again, do not multiply those together and get 80. Instead, you have to do these two things. When you're working with the square root of -20, you have to write that as I times the square root of 20. Now, if you're dealing with the square root of -4, you can go ahead immediately if you want to and just write that as 4i. Then we've got a real number, square root of 5, in the denominator like that. Okay, now what I'm going to do is I'm going to break this up like this. I'm going to write this as I times the square root of 4 times square root of 5 times 4i over square root of 5. Okay, and then just kind of observe what's going on the problem. So you could cancel out the square root of 5, so we don't have to worry about rationalizing anymore. And then if you put this all together, we would have I times I is going to be I to the second. Square root of 4 is going to be 2. And then we have the 4 like that. So that will give I squared is -1. And then 2 times 4 is 8. So we would have -8. And then we would write that as -8 plus 0i in our complex number form. Okay, so one other thing I wanted to talk about just a little bit to kind of finish this up is if you were going through and doing this this last problem, I think I made a little mistake on that last problem. I just noticed what I did. I wasn't paying attention very good to this. The square root of -4 is 2i. So let's get that corrected. I totally botched that one up. So let's get this right. Okay, so when I do this, I've got square root of -4 is 2i. So I'm going to put that, just kind of get everything back in here. So I've got 2i here. So I times I is I to the second. Square root of 4 is 2. Then I have the 2 left over. So I should have got -4 times I or -4. So I write that as -4 plus 0i would be the answer to the problem. Okay. All right, so let's see. I was just going to kind of show you, this is a nice diagram to show you about complex numbers and other number systems that are subsets. So the real numbers are a subset of complex numbers. All complex numbers have a real part to them. So the real number system is a subset of the complex numbers. And then the real numbers can be divided into the irrational numbers and the rational numbers. Irrational numbers would be things like square root of 2, pi, e, things where you have decimals that go on forever without a repeating pattern. Rational numbers are going to be things where the decimals have a repeating pattern, or just fractions, any type of a fraction. A ratio of two integers is going to be a rational number and so forth. And then integers are going to be numbers we've talked about like -2, -1, 0, 1, 2, and so forth like that. Whole numbers are 0, 1, 2, and so forth. Natural numbers are 1, 2, like that. So this just is kind of a nice diagram. It kind of looks like a football. of the number systems that you're familiar with: natural, whole, integers, rational, irrational, real, and complex, and how they relate to each other. Okay, so that will finish us up and give a pretty good review of how imaginary numbers go.